about section 1.2. Section 1.2 is about the graphs of function and several other properties of functions. So as I indicated earlier, a graph can be represented, a function can be represented by a graph. So what do you mean by a graph, first of all? By a graph you mean, if this is, let's say, sorry about that, XY plane be like this, then if I draw any line like that, that's a graph. Okay, so could be straight line, like this is a graph. Could be something that we call a parabola later, that's a graph. See, it could be a circle is a graph. So any kind of line that you draw in XY plane is a graph. So how could a graph represent a function? So that's the question we're going to answer in this section. Okay, and of course if I have a function, we can always represent it by a graph. So as I said here, a function can be defined by a graph in XY plane. In this case, so if you have a graph, so and you know it's a function like this one, this is a graph and it is a function. I haven't told you how to determine whether it is a function yet, but I'm going to choose one which is a function for the time being and show you how you can use a graph of a function to tell what the output value is for a given x value. For example, you see this graph here, and I have this table on the left side, and I have chosen some x values or input values, and we're going to determine what the corresponding y values are. Clearly, I don't have an equation. I don't have an equation for the function to put these numbers in it and compute the y value. So somehow I have to use this graph to see what the y value is. And that's exactly what this sentence tells you. It says, in this case, the output value of y0 for the input value x0 can be obtained by starting at x0. From x0, draw a vertical line and continue it until you get to the graph and intersect the graph. From that intersection point, draw a horizontal line and go toward y-axis, and wherever you end up on the y-axis, whatever that number is, would be an approximation for the value of corresponding y. Okay, so let me show you what I mean by all of these. Let's say you want to compute the output value for x, input value x equal to -2. It is -2 right here. So if I can find my meter stick here, I don't really need it. Anyway, from this input value, because the graph is on the above it, so you just go up like this until you get to graph. So I'm going to put an arrow that I'm going this direction. Then I got to this point. From this point I turned right toward y-axis and I go that way. So I ended up with this point, and this point happened to be exactly 3. So this is 3. So this is f of -2. See, that was pretty simple. -1. If I look at -1 right here, -1 is exactly on the graph. So if I move toward the graph, I get to the same point. So in other words, what it says, the y value at any x value is the height above that x value under the graph. You see this height here, which is 2. The height is 3, is the y value. Here the height is 0, so this is 0, so f of -1 is 0. At x value 0 right here, if I move down toward the graph, I end up right there, and if I go horizontal, I would be at that point. So this is -1. So this is f of 0. And if at 1, again, the height is 0, because if you go up to the graph and going horizontal to the y-axis, you're always going to be at this point, which is 0. So this is f of 1. Then at 2, here's 2. If I go up to get to the graph, this direction, and then turn left toward y-axis, I get to 1. So you get 1 right here, and this is f of 2. And finally, for 3, if you start at 3, going up, and then turn left toward y-axis, you get to 2. So you get 2. So this is f of 3. Pretty simple. So we can find, you can use the graph to find the y values. That's not difficult. But the point is that how do I determine whether a graph is a function? To do that, we use the so-called vertical line test. Vertical line test says that if you have a graph like this graph right here, which in calculus we call it a cardio because it looks like a heart. And then if I choose an x value, an input value, and at this input value draw a vertical line like this, then this vertical line, if I go up or down, it will get you to 2 different y values, y1 and y2. So I have a y1, the x value is a because you are on this line, and a y2. So as you can see, the same input value a has 2 different y values. So this is not a function because one x value has 2 different y values. So that suggests the following: if you want to determine whether a graph is a function, and if at this one vertical line intersect the graph at more than 1 point, the graph is not a function. So I said it a little bit differently here. First of all, only certain type of graphs can be used to define functions. The vertical line tests assert that a given graph is a function if every vertical line intersects the graph at 1 point only. If one vertical line intersects at more than 1 point, like this one here, of course there are more vertical lines that intersect at more than 1 point, but if you can find one line that intersects at more than 1 point, then that graph will not be a function. Okay. So as I said here, this line x equal to a, this vertical line intersecting at 2 different points, therefore makes this graph cardio not to be a function. So using that idea, we're gonna determine which one of these 6 graphs represent a function. We have 6 of them. So if you draw a vertical line here, let's say I draw a vertical line at this point right here, see this vertical line intersecting at more than 1 point, so not a function. Here if you draw any vertical line, you see you get 1 point. Of course there are some line here, this line actually do not intersect the graph at all. These are called asymptotes. So this is a function. Every vertical line, you see, intersect at 1 point. This is not a function because if I draw, let's say, this vertical line, you see, you get more than 1 intersection point. So this is not a function. This one is yes, because if you draw any vertical line, no matter what, it's always having 1 intersection point, so a function. So is is this one? A function. This is not a function because if I draw this vertical line here, see, you get 2 more than 1 intersection. Not a function. This is, see, if I draw this vertical line, you get 2 intersections. Not a function. This is, if I draw a very vertical line, you see, a function. This is also a function. So some graphs represent function and some graphs do not represent any function. You see. Okay. This section is going to be a rather long one. Several different concepts involved. Okay. The next thing we're going to discuss is how to sketch graph of a function. Well, the quick answer is I use my graphing calculator. Well, we know that, but the point is that we're going to understand how, at least for now, to graph without the graphing calculator. And then in long run, later on, we use our calculator. But the idea is to understand the concept of graphing a function. And that tells us a lot more about the function. Because graphing a function without a calculator could be really tedious. So what I'm going to show you here is to, by some simple example, discuss the idea, at least for 2 functions, and then in long run for the future and the rest of the book, we're going to use a graphing calculator to graph a function. Okay, so to graph a function without a graphing calculator is actually the idea is really simple. The idea is to draw a table of values like this, put x here, y there, and then choose several values for x, like x1, x2, x3, xn. The more the better. And then put these values of x into your function to get the y values. And then go ahead and plot order pairs. So each one of these pairs will give you a point like this. And then after that, we just kind of draw a line through those points like that. Then that gives you the graph. So the idea is simple, but what you get is not really all that accurate, and this technique is not efficient because you don't know what x values to use and how many x values to use. So the idea is to use as many as you can. It would be easy to use this technique if you have a prior idea about the shape of the graph. For example, if you know your graph is a straight line, all you have to do is to find 2 points and then connect them, you get the whole thing. See? Or if you know your graph is a so-called parabola that we're going to study later, and then you have these points like these, and then if you know it's a parabola, then you draw a nice parabola to those. Okay. And if you have no idea how the graph looks like in advance, then this technique of graphing really is not an efficient way to do it. So we're going to use a graphing calculator in the future, but let's understand the idea. So as I said, get a table of values. Like here, if I want to graph this function here, I have a table of values, and I have some values for x, -2 to +2, and I want to find the y values and then plot them here. Okay. let's see. If I put x equal to negative 2, you see in this function, f of negative 2 is 3 times negative 2 minus 1. You get negative 6 minus 1 minus 7. So minus 7. If I put 1, get f of negative 1. So 3 times negative 1 minus 1. Minus 3 and minus 1 is minus 4. So minus 4. If I put 0, you get f of 0. F of 0 is 3 times 0 minus 1. You get minus 1. And f of 1, you have 3 times 1 minus 1. You get 2. And finally, f of 2, you get 3 times 2 minus 1, you get 5. Okay, so I have to plot these points, 2, negative 2, negative 7, negative 1, negative 2, and so forth. Unfortunately, the units on y values are too big here, the division. So I'm going to get rid of these and rescale them so I can actually do this. So I'm going to call this one 1, then 2, 3, 4, and 5. So negative 1, negative 2, negative 3, negative 4, negative 5, and negative 6 is right here. Actually, this is positive 6. Okay, so then point negative 2, 7. I have negative 2, 7 is way up, negative 7 is way down here, so I really cannot plot this because I don't have room. Okay, so I'm going to continue with the second one. Negative 1, negative 4. Negative 1 is right there, and negative 4 is here, so it gives me this point. Negative 2, negative 4. That. 0, negative 1. 0, negative 1 is actually right here. 0, negative 1. 1 to 2, this is 1, and then 2 is right there. 2 and 5, this is 2, and this is 5. Now if you step back and look at this point here, 1, 2, 3, 4. If you look at these, the most reasonable curve that you can run through these points is a straight line. You see, if I connect these like this, it's the graph of this function. You see, in fact, I knew that it's going to be a straight line because this is a so-called linear function. So I know in advance that this graph is a straight line, so I really didn't need as many points. All I needed was 2 points to graph it, but it doesn't matter. I had more points. It should be okay. Now if you want to actually this graph with your graphing calculator, what you do, you go to clear these up. So I would graph 3x minus 1. We just type it. Go to y equal to, you get to this menu, 3 times x minus 1. Okay. Now, what window I want to use? This window, x goes from minus 10 to 10, y from minus 3 to 3, so I'm going to change this to minus 10 to 10. This is a standard window. Sometimes you start with this window and then you change it in order to get your graph to show its essential features of it. Okay, so in this case, I think this window should be okay. So if I say graph see, the graph basically looks like what I have on my paper. Okay, so the second example, this is going to be a function later on. We're going to call it a quadratic function, and the graph is a parabola, but I'm not going to say it now. Okay. So let's look at the values of x and see what the y values is. So f of g, in this case, g of negative 2 is negative 2 squared minus 2 times negative 2 minus 3. So negative 2 squared is 4. Negative 2 times negative 2 is also 4 minus 3. You get 8 minus 3, you get 5. So you get 5 right there. So maybe I should go ahead and plot as we go. Points negative 2 and 5. Again, I'm going to rescale these numbers here. This is a little bit too big. So I'm going to call this one 1, 2, 3, 4, and 5. Minus 1, minus 2, minus 3, minus 4, and minus 5. That's better. So point negative 2 and 5 gives me this point. Okay. Then g of negative 1. G of negative 1 is negative 1 squared minus 2 times negative 1 minus 3. So if I work this out, I get 1 plus 2 minus 3 is 0. So at negative 1 you have 0. It's going to be this point right there. So this point is actually the other. Negative 2 and 5. This is negative 1 and 0. Okay. F of 0, g of 0. G of 0, that means I replace x by 0. So 0 squared. Use a different color, so this kind of do not mix. 0 squared minus 2 times 0 minus 3, you get minus 3. 0 minus 3, 0 minus 3 is right here. Use the red. And g of 1. G of 1 is 1 squared minus 2 times 1 minus 3. I would get 1 minus 2 minus 3, you get minus 4. So at 1 you have minus 4. So at 1 this is minus 4. At 1 is right here, you see. So I have this point, this point, this point, and this point. One more to go, so this is minus 4. G of 2. G of 2 is 2 squared minus 2 times 2 minus 3. You get 4 minus 4 minus 3. You get minus 3. So at 2 you have minus 3, which is right here. So that's all points we have. So it seems to me, if you, as you said, what is the most reasonable curve that I can, that you would be able to run through these points? So to me, you see, I start here and go down all the way. I have to curve it in order to go to all these points. Curve it and then go here, and then it turns back up and goes up there. So it seems like it's something like this, and then it has to go up like that. You see, that would be the graph of this function, which is if we call it later on, we're going to call this a parabola. So let's do it with the graphing calculator to see if we actually got it right. So let's see if my calculator will show. Maybe I can turn on the slide. x to power 2 minus 2 times x minus 3. And again, I'm going to use the same window I have to see what happens. So if I, oh, I didn't put the exponent, 2. So x squared minus 2x minus 3, then I say graph. You see? It's similar to what I have on my paper. Okay? So this is the idea of graphing a function without a graphing calculator. But as I said, in the future, we're going to just use our graphing calculator to graph functions. Well, I recorded this once but didn't have sound, so I have to redo it. Sorry about that. The idea is to find the domain and range of a function graphically. How do I use the graph of a function to determine the domain and range? Of course, we learned before how to find domain from the equation of the function, but we couldn't find the range. So the good thing about using graph to find domain and range is that we can find both of them, domain and range, and it's much quicker. Okay, so the best way to show that is to do it by example. You see, I have this function here. Forget about all this red and stuff. Just look at the graph here. So this graph starts at this point and ends here with 2 solid points. So I have one single piece. So what I would do, the first thing I would do, go from the left endpoint, and then from the left endpoint I drop a line to x-axis to see what I get on x-axis, which is -2. From the right endpoint, also I drop a line, I get to x-axis, which is 1.5. So that means this graph involves the values of x-axis between -2 and 1.5. So the domain is -2 to 1.5. This piece right here. For the y values, I go to the lowest point. From the lowest point, I go toward y-axis, I get -3. And then from the highest point, I go toward y-axis, I get 5. And as you can see now, the y values involved are between these two numbers, -3 and 5. So your range is -3 and 5. So let's use this idea. Again, as I said, I did this once, and you may have a variety of situations here. Let's say I have something like this. You see, if I have a graph, the left endpoint is hollow and right endpoint is solid, then when you get your left endpoint and right endpoint, then the domain is from -2 to 2. For example, here this is 1 and 2. But this is hollow point, so I use parentheses, and then this one is solid point, and I use bracket here. So that's a domain. Then for the range, if I go from lowest point is, let's say, -1.5 right here, to the highest point is 3. So the range would be between -1.5 to 3. So the range is -1.5 to 3, but parentheses, hollow, because this point is not included. Now if you have situation like this one, that you have a, let's say, solid point here on the left endpoint, but there is no right endpoint. This one goes forever. So that means the x value of the right endpoint is at infinity, and the y value of the right arm is also at infinity. Okay, so the domain is, let's say, I go from the left endpoint, I get to -2. This is -1, -2. So I go from -2 domain to infinity. Would be all of this line, and then the range, I go from the lowest point, which is -1, to infinity, which is all of that. See, Now if you have a situation when you don't have any solid point or hollow point and you have arrow here, that means the graph goes forever, then in that case domain and range would be a whole real line because all the endpoints are at infinity. So it depends on actually what the shape of the function is. So if I use these ideas here for the next example, you see you have this nice looking graph here given to us. It starts at the solid point 0 and then it goes forever to the right. So if you go from the left endpoint, go down, you get to -5, and then the right endpoint is at infinity, so the domain is all of this real line here, so -5 to infinity. If you do the range, you go from the lowest endpoint. If I go to lowest endpoint, you see it is -4, and the highest point is 4, so the range is from -4 to 4. It's all of this line right here. Okay, and a couple more ideas, like f of x is given to be 4. I want to know what x value is. So how do I find the x value whose y is -4 from the graph? So what I would do, I start with y equal to -4. You see, this is y equal to -4 right here. Then I go horizontally toward my graph. So when I get to the graph, I go either up or down toward x-axis. So whatever number I get on x-axis is the x value we are looking for. In this case, going to be 2. So this is the arrow. You see, I start with -4. Then I go up to the graph, so I get to -2. So x equal to -2. For the other one, y equal to 3 is right here. This is y equal to 3. If I go horizontal to get to the graph, I have to go to both sides. You see, I have to go to the right and to the left. See, if I go to the right, I get to this point. So if I go down, I get to this point, x value. So it's 0.75. This is one value. I also have to go on the left side. If I go that way and then go down, I get to this point, which is -0.75. So it's 0.75 and -0.75. Two values. So these are the x values whose y value is 3 for both. Now if you want to find the domain and range of this function here, first you graph it on your graphing calculator. See, I did this already, so see, I typed it in, x to the 4th minus 12x squared plus 4. So see, if I graph it on window, standard window, -10 to 10, -10 to 10, the graph, actually you cannot see all of the graph because it's chopped off on the bottom, but we need to have most of it. Okay, so I have to adjust my window so I can see all of this. So I go to window, and the negative y value, I go from -40 to see if that will do the trick. So -40 to 10. So see, now I can see where the minimum point is. So as you can see, the arms of the graph both go to infinity. That means the left endpoint and the right endpoint on x-axis are infinity. So that gives you the domain -infinity to infinity. But for the range, you see, you go from the lowest point that I have to determine what it is to highest point, which is infinity. So the best way to get the lowest point, there is another way to do it. We do it later. But for right now, I'm going to use the feature called trace. You see, so you see here it says I'm not on the graph, so I push on this arrow. Yeah. You see, you are on the graph now. I'm going to do it again. This is graph, go to trace, then push. You see, here I should give me the equation of the graph. So if I push that, you see, I see the equation of the graph. Then with this arrow, I start going down. and I look at my y values. As I look at my y value go down, see it getting smaller. You see negative 31.72. If I do one more, negative 31.73, and if I push one more, it starts going back up. So this point actually is the lowest point, negative 31.73 to infinity. So that would be my range, negative 31.73 to infinity. Okay. So the next concept is the concept of x-intercept and y-intercept. The y-intercept of a function is the y values of the point when the graph crosses y-axis. For example, if you have this green graph here and it crosses y-axis at this point, so let's say this is 1 and 2, so this x value is 0 but the y value is 2, so that means your y-intercept is 2, which is f of 0. Now if I have this red graph and crosses y-axis at negative 3, so the x value is 0, y value is negative 3, so that would be your y-intercept. So that means that if you want to find your y-intercept, you always replace x equal to 0 in your function equation and determine what you get for the y value. For example, here we have f of x. So y-intercept is f of 0. So if I replace x by 0, I get 3 times 0 minus 1. 3 times 0 is 0 minus 1, you get minus 1. So that's your y-intercept. That means this function, whatever the graph is, crosses y-axis as negative 1. Okay. Now we're going to do x-intercept. Well, x-intercept is actually is what we call a zero of a function. A zero of a function is actually the x value whose y value is 0. You see? So if I have something like if I have a function and I have a point on it which is like say 5 and 0, you see the y value is 0, so 5 is called a 0 of a function. If I have negative 3 and 0, then negative 3 is a 0. It doesn't mean that 5 is 0, it means that x value of 5 has a corresponding y value of 0. Okay. But sometimes these x values are complex, sometimes they are real. Okay, so a 0 of a function could be a real number or a complex number actually. So, but if that 0 of the function is a real number, is actually an x-intercept. So 0 is more general than x-intercept. An x-intercept is a 0 of a function, but a 0 of a function may not be an x-intercept. So when I graph a function, let's say if I have a function like this, and then I graph it and we get something like that, you see, you are crossing all these points. Okay, these are actually x-intercept. You see, I call this one x1 and 0. So notice that the y values are 0. x2 0, x3 0, x4 0, and x5 0. And these are actually real numbers, so these are x-intercepts. So I have 5 x-intercept. Okay, if you have a 0 which is complex, then that complex number is not going to show on a real line anymore. Okay, so here's the idea again. If you have a number, whether it's real or complex, and whose y value is 0, then I call that number a 0 of a function. So a 0 of a function is an x value for which the y value, y equal to f of x, is equal to 0. a zero of a function, as I just mentioned, could be a real number or a complex number. If if a real zero of a function is called an x-intercept, okay? And when you graph it, you can actually see it. You see, these are the real zeros, and as a result, we call them x-intercept. And notice that the y value is 0. So that would tells you that if you want to find x-intercepts of a function, then just replace y by 0 and then figure out what the x values are. And that comes down to solving some equations. Of course, if you have the graph, that's very easy to do. You see, like here, you see, in this case, I have this graph. I want to find x-intercept and y-intercept. Y-intercept is clear, it's right there. This is the y-intercept, which is 1. See, so y-intercept is 1. How about x-intercepts? X-intercepts are the points of crossing x-axis. So I have one right here, one right here, one right there. You see? So I have 3 x-intercepts. So x-intercepts are -2, and this is 1, and then 3. So these are the x-intercepts. And these are real zeros. Real zeros. Or x-intercepts. So x-intercept and real zeros are the same. But if the zeros are not real, then you don't call them x-intercept. You call them x-intercept only if they are real numbers. Okay. So what we're gonna do? We're gonna do without the graphing calculator the x-intercept of these functions. So to do that, we know that the y value is 0. So set y equal to 0. Of course, this is y equal to that. So that means I put f of x equal to 0, which is 3x minus 1 equal to 0. And now, if I add 1 to both sides, I want to solve for x. Then I get 3x equal to 1. And if I divide by 3, I would get x equal to 1/3, and that's your only x-intercept. Okay, and is that this your only 0? Okay, this is your 0. 0 of f of x, and is real. So is x-intercept. This one, put y equal to 0. Of course, this is y equal to that. Then it is red. So that means I have to put x squared minus 2x minus 3 equal to 0. Now you have to solve this quadratic equation. You see, back to quadratic equation. Remember, ax squared plus bx plus c. I use quadratic formula. Sometimes you can factor. If you can factor, you don't have to use quadratic formula. So in this case, I can factor actually. This is x minus 3, x plus 1 equal to 0. Because if I multiply this out, I get that back. Okay. So if I put this one equal to 0, I would get x equal to 3. If I put this one equal to 0, I get x equal to minus 1. So 2 zeros. 2 real zeros, so 2 x-intercepts. So these are x-intercepts. The next one is already in factored form. So if I put y equal to that, set y equal to 0, that tells you x plus 1 times x minus 3 times x squared minus 4 equal to 0. And because it's factor form, I have to put each factor equal to 0. So x plus 1 equal to 0 would give me x equal to -1. This is one real 0 or x-intercept. This is real. X minus 3 equal to 0. This would give me x equal to 3. This is also real. And then x squared minus 4 equal to 0. gives me x squared equal to 4. So x, if I take square root, I get plus or minus 2. So 2 more real 0. So 4 x intercepts. Minus 1, 3, 2, and negative 2. So 4 x intercepts. 4 zeros actually, 4 zeros, but they are real, so that we call them x intercept. Real zeros are x intercepts. But finding x intercept is an easy concept, but it turns out to be sometimes more challenging than it is, because when you put f of x equal to 0, then you have to solve this for x. Then solving this for x without a graphing calculator becomes really tedious sometimes, because you have to factor, and you may not be able to factor, so it's going to be very difficult. So if we can find x-intercept algebraically without a graphing calculator, fine. But if you can't, then we can just use a graphing calculator to approximate the zeros, you see. So if solving f of x equal to 0 turns out to be difficult, then we utilize a graphing calculator to estimate the real zeros. Okay. A graphing calculator does not identify the complex zeros, because complex zeros do not show on xy plane. Only real zeros, which are x-intercept, show. Okay. For example, if you want to find x-intercepts of this function here, you have to put it equal to 0. So I say q of x equal to 0, which is x to the 4th minus 5x cubed minus 5x squared plus 23x plus 10 equal to 0. Now we have to solve this baby, and very difficult to solve. So what we do it graphically. To do it graphically, basically the idea is this. The idea is to graph it, whatever the graph is, and then ask the graphing calculator to tell us what the x values of these points are. That would be, these are your x-intercepts. Okay. So let me show you how that works. So the first thing you gotta do is to actually graph this function on your graphing calculator. So x to the power 4 minus 5x to the power 3 minus 5x to the power 2 plus 23x plus 10. Okay. So let me see if I typed it right. 10, 23 minus 5x squared minus 5x cubed and x to the 4th. Yeah, I typed it correctly. So say this is the window I have. So let me see if this window will do the job. If it doesn't, then I have to adjust it. So say graph. Actually, it's okay, almost okay. A little bit chopped off on the top and a little bit chopped down on the bottom, but I can see the x-intercept, you see. So all I really need are these x's, these x-intercepts, these crossing points. So I really don't have anything to do with high point and low point. So what I can do, I can adjust my window a little bit to bring it to the center a little bit. So I go from that, and I don't need all of these x values here. So I'm going to make the graph a little bit bigger. So I go from minus, let's say from minus 6 to 6, and then instead of minus 40, you go from minus 20 to 20. That should be good enough for this purpose. You see, As I said, I really don't need the high point and low point. I just need these x values. Okay. So maybe I can push it to the left a little bit to get a bigger x value. So instead of 6, I say, let's say 8. Okay, this is good enough. So what you do, you go to math, here math, I'm sorry, go to calculus, you see calculus, C-A-L-C, so I have to say second trace, so you say second trace, you get to this menu. Then the second item says 0, that's what we want to find, 0, so choose second item here. Then I want to start with this point, so what you do with, see, with this cursor, move the cursor all the way, because it says left bound, you see left bound here, it says left bound, so I'm going to put this cursor on the graph so that it would be to the left side of this x-intercept. You see, this is the x-intercept, and I'm going to put it on the left side. So it's on the left side, I say enter. Now it says right bound. So if I move it down, you see now it's on the right side, you see, and I say enter. Now it says guess. Now I put it between the left and right, and I guess I just say enter. You see, your y value is 0 and x value is -2, so one x-intercept is -2, so I say x-intercept -2, this is 1. I have to do this for this point, this point, this point, 3 more times. So I go to calculus, which is second trace again, go to number 2, and then move this cursor to the left side of this point. You see, now I want to do this point, so I put it on the left side, say enter. Then move it to the right side. You see, it's on the right side now, say enter. Then it says guess, enter. So your y value is 0 and your x value you have to approximate about -0.41. That's what I would say. So I would say -0.41. Okay. 2 more to go. The next one is this one. So I say second trace, number 2 zeros, and then I just continue moving this cursor. You see on the left side, left bound, enter, move it to the right side, right bound, then guess, enter. It gives you y equal to 0 and x is about 2.41. So 2.41. So these are approximate, you see. They are not exact. The first one was exact, but the other 2 are not exact. 1 more to go. Second trace, number 2. On the left side, say enter. Now you are on the right side, enter, and then guess. You get x equal to 5. So these are your x-intercept by graphing calculator. Much easier to do. Okay. The next, so from now on, if you cannot do it algebraically by calculations, then you do it by your graphing calculator like the way. We're gonna do one more here. Let's say this is a function. You're gonna find both, I mean the real zeros both, or zeros, x integers or real zeros both, algebraically and graphically. So if you want to do it algebraically, so algebraically, set f of x equal to 0. So that means I have to put x squared minus 6x plus 8 over 3x equal to 0. And to solve this, I multiply both sides by 3x to get rid of the denominators. So if I do that, it's 3x on the left side. So this 3x cancels this 3x on the left side. I would get x squared minus 6x plus 8 equal to 0 times 3x, you get 0. Actually, when you put a fraction equal to 0, put the numerator equal to 0. That's the easiest way to do it, instead to avoid all these calculations. For example, if I have something like, let's say, a over b equal to 0, all you have to say a equal to 0. You see? So if I have this fraction equal to 0, I put the numerator equal to 0. And now I have to solve this equation. I think you can use quadratic formula or factorization. In this case, you can factor. You see, x minus 4 times x minus 2 equal to 0. Again, if you want to, you could have used quadratic formula. Where did I put it? I'll show you one more time. I don't have it here. You see, I can use minus b plus or minus b squared minus 4ac over 2a, but I don't have to do that because I can factor much faster. So if I put this one equal to 0, it gives me x equal to 4. This is one x-intercept. Put this one equal to 0, it gives me equal to 2. Okay. I could use quadratic formula. So let's, for the sake of this, maybe I use quadratic formula. You see, x equal to, so in this case, you see, your a is 1, b is negative 6, and c is 8. So if I put these numbers in quadratic formula, see, I get the same numbers, just for the sake of demonstration. Minus b minus 6 plus or minus square root of minus 6 squared minus 4 times a, which is 1, times c, which is 8. Okay, divided by 2 times a, 1. So I'm putting them in this formula, you see, minus b. Then if I continue this, negative times negative, positive, plus or minus 36. 4 times 8 is 32, and this have a minus, so minus 32 over 2, and this is equal to 6 plus or minus square root of 36 minus 32 is 4 divided by 2. So you have 6 plus or minus 2 divided by 2. So if I use plus, 6 plus 2 is 4 divided by 2. 6 plus 2 is 8 divided by 2, you get 4. 6 minus 2 is 4. 4 divided by 2 is, you get 2. And these are exactly the same numbers I got here. So as you can see, if you can factor, it's a lot more easier. Now let's do it graphically, and to see if we get the same numbers graphically. Okay. So first you have to type the equation in your calculator. So if you, every time you have a fraction, put them in parentheses. Put the numerator in parentheses, x to the power 2 minus 6 times x plus 8. Divide that by parentheses 3x. That's the right way to do it. Because I already know x-intercept here, so the window, I think this window would be good enough. Let's see if it's good enough. If it's not, I change it. So let's say graph. See, it's kind of tricky a little bit. You see, maybe this is really not. So this window, the y value is pretty bad. So I go from minus 2 to because see, it goes, as we can see, it goes below x-axis and then moves back up. So it goes, crosses x-axis at 2, goes below, and then comes back up at 4, actually. So to see it better, actually I can change my window a little bit. It'll go from -1 to 1, actually, for y value. You can see the phenomena a little bit better, you see. This is one x-intercept, this is another one. So to find them, go to second trace, the number 2, I guess I'm going backwards, so let's see. You see, it's coming down. It's on the left side, say enter, then I move it down here, on the right side, enter and enter, you get 2. This is this number right here, you see, 2. Now if I continue second trace, number 2 again, put it on the left side of this 0, left, right, enter, you see, 4. So we got the x-intercept both graphically and non-graphically. So I'm gonna stop here at this point, and I come back to it in next video. Alright, this next concept involved is idea of local minimum and local maximum. So basically what we have, if you have a function, let's say I have a graph that looks like this, okay, ups and down. Here is a high point, here is a low point, here is a high point, here is a low point, and so forth. These are called local maximum. You see, this is local maximum because if you restrict yourself to this area, you see, to this locality, so this is the highest point for this neighborhood right here, and this one is the lowest point here for this neighborhood. This is the highest point for this neighborhood, and so forth. But overall, this high point is higher than that. So I have 3 maximums. So these are called local maximum and 2 local minimums. So local maximums and local minimums means high points and low points. Okay. So basically, like here it says, a function has a local maximum of y equal to f of c. So here's, if I have, just say this is c, call it C1. So C1, the y value, so the x value is C1, the y value is f of C1, the high, the maximum value. You see, this is f of C1, whatever this height is. And you have another maximum here, C2. F of C2 is the locally the highest point. So this point is C2 and f of C2. That's C2 and f of C2. C1 and f of C1. So this point is locally is the highest point. This point locally is the highest point. Similarly, local minimums. So if I call this one C3. So this point here would be C3 and f of C3. So this point is the local minimum, and this point is the local minimum as well, and so forth. Okay. So the function has a local maximum of y equal to f of c at equal to c if this point is locally the highest point, or if this point is locally the lowest point, we call it a local minimum. Okay. We're gonna find these points actually. So what we like to know, I want to know the x value and the y value. You see, you want to find the x value of y value of this point. You want to find. So let me just do another one here. Let's say this C1, C2, C3, C4 are, and together with their Y value. So C1 and F of C1, C2 and F of C2, and so forth. Okay, so we're gonna find. And actually, if you want to do these points for this class, the only way you can do it is do it graphically. If you want to do it algebraically, that would be a topic in calculus, and we're not doing calculus, of course. So what we have to do then is, if you have a function, you want to find the local minimum, local maximum, you simply graph it on your graphing calculator. Then I'm going to show you which feature of the calculator that you would use to find the coordinates of local minimum, local maximum. Like for this next example, we don't have to do that because we already given a graph, and I want to find the local minimum and local maximum. You see, I have a local minimum here, and another local minimum and a local maximum. So if I say local minimum, so local minimum, one of them is this point, so x value is -1, and the y value is -2. So -1, -2 is 1, and the other one here, you see, is 2 and -1.5. So this is 1, 2, this is 1.5. So -2, this is 2 and -1.5. 2 and -1.5. So these are the local minimums. Local maximums, we have one local maximum only, this one, and that's at this point. You see, this is the x value, this is y value. X value is 1/2, y value is also 1/2. So local max is at 1/2 and 1/2, and that's it. Now if you want to find one like these, you do it similarly, but you don't have the graph, but that's okay. Just find the graph on your graphing calculator and figure out. I'll show you how they look, what the local minimum maximums are. Let's say this one. So let's graph it first. So I go to y equal to, instead of that one, x to the power 2 minus 2x plus 2. Actually, this window that I have is not a good one. You see, you don't see very much. Actually, you don't see anything. See, because that window is too small to show anything. So I go to zoom 6. If we go to zoom 6, it gives you the standard window -10 to 10, +10 to 10. So now you can see that. And if you want to make it a bit bigger, you can adjust your window. So I don't have to go from -10 to 10. Actually, I can go from minus maybe 4 to 4 for x value. You see, it's better. But I'm going to change this a little bit. -10 to 10 for y is a little bit too much. So I go from maybe -3 to 3. Actually would do a better job, you see, like that. So because I want to find the local, that's the only local minimum. There is no local maximum, only local minimum. So the question is, how do I find this local minimum by this calculator? Again, go to calculus. That's where we went for x-intercept calculus. So you go to second trace. Now here I have minimum, maximum. You see, I have to use minimum. Third item, minimum, and is asking for the left bound. That means move this cursor to the left side of the local minimum and say enter. And now he's asking for the right bound. Move it to the right side and say enter. Now it says guess. So you see there are two markers here, and your local minimum is in between. So say guess, enter. You see, the y value is 1, and the x value is 0.1999999, is almost 1. Okay, so here I would say local minimum is at 1 1. You see, one and 1. This is 0.999986 is almost 1, because it's approximation after all. And there are no local maximum, so none. The second one, again, there must be, I'm sure there are more than one local minimum, local maximum. So go to y equal to, type this 2x to power 4 minus 17 x plus 19 x to power 2 plus 80 x minus 84. If I use the window that I have here, it's not going to do the job. You see, if I say graph, really not showing very much of it, so I have to make my window much bigger so I see more of the graph. So I'm gonna go from minus, let's say 10 to 10 for the time being, and y value I go from minus 10 to 10 as well to see what I get. Minus 10 to 10. Still not very much of anything. So go to window, go from, let me change this one, go from minus 50 to 50. You see what we get actually. You see y-intercept is minus 20, so window, just have to play with it. From minus 10 to 40, or from minus 100 to 100. See what happens. Really, this is 40 is too much, so go to 10 and make this one to minus 30. What happens. Okay, I have something on the left side. Did I type it right? Oh, I did not type it right. That's why I'm not getting it. Sorry about that. You see, I have 17x cubed. I did not put cube for 17x cubed, so I have to say here, second insert to power 3. That's better. Now I type, so sorry about that. You see, 2x, let's do that again. 2x to the 4, let's see. You see, 2x to the 4 minus 17x cubed, fine, plus 19x squared, okay, plus 80x minus 84. That's much better. Let's say graph to see what happens. Actually, this window is not good, so let me, yeah, okay. So I'm gonna go from let's say minus 5 to 5. Minus 5 to 5, and let's say graph. Yeah, I'll get it a lot better. You see, a little bit chopped down. I have to get it, and then also x value. So x value 5 is not enough. I put 10 and 150. You see what happens. Minus 5 to 10. Oh, minus 150. Okay. You see, this is the graph I have. Okay. So as you can see, I have two local minimums and one local maximum, which is very much similar to the one I did here. It's not exactly the same thing, but similar to it. So to find x-intercepts, I mean the local minimum, I go to second trace. So you go second trace, I go to number 3, and I'm going to start with this one. Put it on the left side. You see it's on the left side right now of this minimum. Enter. Put it on the right side. Enter and enter. So I have one local minimum at almost negative 0.9 and negative 126.9. So local minimum negative 0.9 and minus 126.9 is one of them. Then there is another one. So let me find the local maximum. Just find them in a row. So second trace, number 4 maximum. So I just continue this to this point. Put it on the left side. Enter. Put it on the right side. Enter, and then guess. So local maximum is actually 2.23. 2.23 is x value and 49.8. It's a local maximum. I have one local minimum to go. See, I did these two. So second trace one more time. Go to number 3 and continue this. Left endpoint, enter. Right endpoint, enter and enter. You have 5.04 and 85.48. So these are the local minimum and local maximum. Okay. Maybe I can make this one red. 2.23 and 49.8. Okay, so this is how you find local minimum and local maximum of a function using your graphing calculator. Okay, now the next concept is the concept of increasing and decreasing functions. Okay, well, increasing means something is getting larger, decreasing means something getting smaller. Basically, as far as a function is concerned, we say a function is increasing if y gets larger when x gets larger. So because x changes, then y will change. So if x gets bigger and bigger, implies that y also gets bigger and bigger, then we say the function is increasing. Or conversely, if x gets smaller, then y gets smaller as well, then function is increasing. Like in notation, we write it like this: if input x2 is bigger than input x1, then the corresponding output f of x2 is also bigger than corresponding output of f of x1. So if you look at the graph of the function, basically what it means, if the function is represented by a graph, let's say like this, then the graph is rising as you go to the right side. If you walk like this, if you walk on the x-axis toward infinity from left to right, and you look at your graph like that, the graph, like a ceiling, it starts going up. See, the heights are getting bigger and bigger as you go to the right. If this happens, then the function is increasing. We say function is rising in the previous course, maybe that's the terminology you used. Function is rising and or falling. Falling is decreasing. So the function is decreasing. If as x gets bigger, that means as you go to the right side, x gets bigger. These are x values getting larger this way. Then the y values also get bigger. So the function, the graph of the function start keep rising up. Okay. If on the other hand, x gets larger, but the corresponding y value gets smaller, they go opposite. You see, for the increasing, the direction of the change is the same. You see, bigger implies bigger. Here, bigger implies smaller. So if that happens, if they're opposite, the function is decreasing. So basically, what happens if you look at the graph of the function? If I do a graph here, you see the graph is falling this way. You see, so that means if you walk toward the higher, bigger x values this way, and look at the graph, the height is getting smaller and smaller. See, so this way the graph is falling, or let's say the function is decreasing. So if the graph keeps going up, the graph is increasing, or the function is increasing. If the graph goes down, the function is decreasing. Okay. Of course, sometimes the graph increases, sometimes decreases. Let's say if you have a situation like this, you have a function whose graph is going like that. This is increasing, and then goes to a maximum point, and then it starts going down, and then decreasing. You see. And then goes all the way to some lower point again, and then it starts going back up. So these are different situations. The graph may always be increasing. As you go from minus infinity to infinity, it keeps going up, never goes back down. Or maybe as you go from negative infinity to infinity, walk that way, the graph is always going down, so it never goes up. But here is the situation, as you walk this way, then sometimes increases, sometimes decreases, sometimes increases, sometimes decreases, and so forth. So this behavior will be different for different functions. Okay. So the point is that if you have, like here, if you have a situation here, if I have a situation here, like this case, this graph is always increasing, so I say increasing on minus infinity to infinity. That means this is the x value. So if your x value goes from minus infinity to positive infinity, that means that if you walk from negative infinity to positive infinity, your graph keeps going up. So it's increasing on the whole real line in this case. But this one, we say decreasing on minus infinity to infinity, always going down. No matter how far you go, the graph keeps going down. But here it's a little bit different. So what we need to do is to say, well, the graph, if you walk from minus infinity all the way to this maximum point, is right here. The x value of the maximum point is x value, call it x1. You see, x1, this point is x1, y1. It's the maximum point, local maximum. So if you walk from minus infinity to x1 on this side, on this interval, is increasing. So I say increasing on minus infinity to x1. And then if you go from x1 to x2, this is the lowest point right here. This is the minimum point. You see, this is x2, and y2. So if you go to, use the green one here. If you go from here to here, you see, on this interval, then you are decreasing. So I say decreasing on x1 x1 to x2, not from. On this interval you are decreasing. I don't care the heights, I just want to know increasing or decreasing. And then if you go from x1 all the way to the end for this particular one, then it's increasing again. You see the function. So maybe I should make this red here, increasing red, then decreasing is green, and then increasing again in red. See? So I said increasing not only on set minus infinity to x1, it is also increasing union from x2 and x2 to infinity, which is this set right here. So in the future, if you want to determine where a function is increasing or decreasing, the first thing you do, you graph it on your graphing calculator, and then like we did before, you find the local minimum, local maximums to figure out the x values of the local minimum and local maximum. There may be 2 or 3 or more, depends upon what the function is. And then just by looking at the graph like this one, you say, okay, clearly the graph is rising over this interval, so it's increasing right there, and also increasing over this interval, so it's increasing over this union, and decreasing in between. Okay, so sometimes it's clear it's always decreasing or always increasing. If a function is neither increasing or decreasing, it's constant. See, so if you have a function that looks like let's say like that, you see, it's decreasing first, here decreasing, and then increasing, and constant the rest of the way. You see, it doesn't go up or down, just continues horizontal, constant. Okay, so it could be increasing, decreasing, or constant. Okay, so with this concept in mind, let's look at some examples here. This example, it says for each of the following functions below, find intervals on x-axis where the function is decreasing, increasing, or constant. Clearly this function is always going down, you see. But this is decreasing on minus infinity to infinity. If you walk, see, on this whole interval here, if I make it red, on this red interval, if you walk on this red interval, you are always, graph is always falling, so it's decreasing on minus infinity, decreasing. This one is the opposite. If you walk on this interval from minus infinity to infinity, the graph is always increasing on minus infinity to infinity. See? The next example, if you walk on this interval here from minus infinity to 1, the graph is increasing. So increasing on minus infinity to minus 1, and then between 1 and negative 1 and 1 on this green interval right here is constant. See? So it's constant on minus 1 to 1, and then starts increasing again. So increasing on not only that interval, also on union 1 to infinity, and of course it's never decreasing. NA does not apply. Okay, so increasing on minus infinity to minus 1, and increasing on 1 to infinity, and of course constant between these two numbers. one is the opposite situation we have. You see, if you go from minus infinity to -1 on this interval, the function is decreasing. And if you go from 1 to -1 to 1 on this one, the function is constant. See? And if you go from 1 to infinity, the function is decreasing. It's never increasing. So increasing on NA does not apply. Decreasing on minus infinity to -1, union 1 to infinity, and the constant on -1 to 1. Okay. The next two, you can have variety of situations. So I try to put as many variety as possible. Like this one here, similar. If you go from minus infinity to -1, function is decreasing. You see. If you go from -1 to 1 on this interval, function is constant. Then if you go from 1, maybe I use blue for this one. If you go from 1 to infinity, the function is increasing. You see. So how do I write that? I say increasing. See, increasing on 1 to infinity on this interval. Constant, decreasing on minus infinity to 1, and constant -1, and -1 to 1. So decreasing on minus infinity to -1, increasing on 1 to infinity, and constant in between. This one is similar. I just changed it a little bit. So I have this interval on the left on which the graph is increasing, and I have this interval on the right, the graph is decreasing, and you have the interval in between where the graph is constant. So you say increasing on minus infinity to -1 right here, decreasing on 1 to infinity, and constant on -1 to 1. Okay, the next example here, as you can see, the function, the graph never rises, never falls. It's always horizontal. That means it's constant. So constant on minus infinity to infinity on whole real line. You see, if you go from minus infinity to infinity, if you walk on this line, you see the ceiling doesn't go up or down. It just stays the same. The next one, like I said before, the graph as you can see, it sometimes is increasing like this up to this point, and then decreases down to this point, and then increases back up. So let's see how we can express this. Well, this is a local maximum, right? A local maximum, the x value is 1. So if you go from minus infinity to 1, the graph is increasing. So increasing on minus infinity to -1 at this interval. Okay. And then if you go from -1 to 1, which is this interval right here, the graph decreases. So I say decreasing on -1 to 1. And then after, I'm sorry, 2. This is my bad. 2. -1 to 2. If you go from -1 to 2 on this interval, you see the graph is going down because this x value is 2. It's decreasing on this interval. And then if you continue going toward infinity from 2 on this interval, the graph starts going back up again. It's increasing. So I say increasing on minus infinity to minus 1. This point was minus 1. And this is 2. And then from union 2 to infinity. Of course, it's never constant to NA. That's not applied. Okay. So that's the idea then. We need to have the graph of the function, and we need to have the local minimums and local maximums, the x values of them. And then by looking at the graph, we can clearly tell where the function is increasing and where it is decreasing. Let's say we're going to do this one right here. So if I can find my calculator, let's see. The first thing I do, I graph this function. So let's see if I can turn this on, makes it difference. That's better. Okay. I'm going to graph this function right here. 3x, negative 3x plus 1. So I say negative 3x plus 1. And this is a linear function. Let's see what my domain is. My domain is really too huge for this. So I'm going to use minus 10 to 10, the standard window. Minus 10 to 10 as well. Then I say graph. And you look at the graph of this function, you see it's always going down. If you go from left to right, it's never go up or down. It always goes down as you go. So this function is not increasing at all. So I say not increasing. Back up, and decreasing on minus infinity to infinity, and it's never constant. You see, so it's always decreasing. The next one, first place to see this. Okay, I guess this is good. Now let's do this next example. X to power 2 minus 2 times x plus 2. Let's just use the same window to see what happens. It's okay, but it's kind of difficult to see what these points are. So I'm going to make the graph a little bit bigger so I can do a little bit better reading around this area, because after all, I have to find the x of this minimum point. I need to find that before I tell where it's increasing or decreasing. Okay, so I'm going to change my window, make my window smaller so the graph gets bigger. So instead of going from minus 10 to 10, I'm going to go from minus 4 to 4 maybe. And the y value, I go from minus 1 to 3. You see, it's much bigger. So I can clearly see the graph sometimes decreasing and then increasing. So if I kind of copy this graph right here on the paper, approximately, it doesn't have to be accurate. So it's something like that. See? Then I have to find this point right here. So local minimum. Remember, I have to find the local minimum. We go to calculus, which is second trace. Minimum, local minimum is number 3. Then we put this cursor on the left side of this local minimum, say enter. We put it on the right side of this local minimum, we put say enter, and then we guess. So it's 1 1. So this point is 1 1. You see, 1 1. So that's what we have. You see, so the graph is decreasing on this interval. It's from minus infinity to minus 1, and then of course increasing this interval. Okay, so how do I write it? So I can go ahead and write it out on my paper right here. I say is increasing, you see, increasing on 1 to infinity. Maybe I should draw the picture right here. See, draw a small picture right there, right here. This, from my calculator, so this point is 1. See, so increasing on this interval and decreasing on this interval. So I say increasing on interval 1 to infinity and decreasing on minus infinity to 1, and of course it's never constant. Okay. The next one is a little bit more evolved, so it doesn't matter. We're going to use our graphing calculator to graph it anyway. So let me see if I can divert this slide here so I can do my graph. Okay, that's a good position right there. So let's go to y, let's clear this up, and then type this function in. 2x to power 4, 2x to power 4 minus 17x to power 3 plus 19 x to power 2 plus 80 x minus 84. Clearly, if I use this standard window 10 to 10, 10 to 10, but it's not. See, this window is no good. You see, it's really, you don't have. So I'm gonna go go from minus 10 to 10 to see what happens. Just go step by step. So it seems like it's going down, then up, then down, goes up. So I have to adjust my y value. So y value, I go from maybe minus 50 to 50 to see if that will do the trick. See, almost have the top part, but bottom part is a little bit chopped off. So I'm gonna go ahead and do a little bit more adjustment. So minus, I say minus 100 and minus 80 to see what happens. Still, you see, a piece of it right there is chopped off, so I have to go further down. So minus 100 is not good enough, so I say minus 150. Here we go. Also my x value, you see a lot of x values here are useless, and so I can go from minus 4, actually minus 4 to 8 for x value would be better. So minus 4 to 8 makes it even better. Perfect, right there. I can see the main feature, and as you can see, the graph clearly decreases to a minimum point, and then increases to a maximum point, then decreases to a minimum point, then keeps increasing. So there are 3 points I have to find. I have to find the x value of this minimum, the x value of this maximum, the x value of this minimum. So what I would do, I want to mimic this graph on my paper here, so I can actually write on it. See? So let's see. I can just do it here first, and then show you. Let me just do this first. be right on it. See? Okay. So what I have to do is to find. Actually, I have to maybe do a little bit of adjustment here. That's better. Okay. So I have to find these x values here. And this x value and this x value. Okay? Okay, here's our graph. And what we need to do is to find the x coordinates of these local minimum, local maximums. So let me make this one a little bit bigger. See? You can see it clearly. This window is not clean. Let me clean up my calculator a little bit so you can see things better. Yeah, that's much better. More. A little bit better. Okay. Now I have to find the coordinates of this local minimum here. You see. So you go to second trace and use number 3. And you have to move this cursor all the way from wherever it is because it's asking for the left bound. So I put it on the left side of this point, minimum point, say enter. It's asking for the right bound. Move it to the right bound and say enter. Then it says guess, say enter. So it's about, the x value is about negative 0.89, so I can round it up to negative 0.9, and that's what I did. You see, negative 0.9. My graph. Now let's move on to the next one, to coordinates of this point. Second trace. This is a maximum point, 4. Then I move the cursor all the way to the left side, enter. Move it to the right side, enter and enter. I get about 2.227 if I round it up to 2.23. As I said, we're not concerned with the y value. So that's what I have, 2.23 right there. See, x value. Excuse me. Then second trace again, number 3 for the minimum. Go to, move it up again a little bit. Put it on the left side. Then put it on the right side. And guess it. You get about 5, you see? About 5. I'll put 5 right there. So this is what I have on my graphing calculator. Okay? Then all I have to do is to figure out where it's decreasing and increasing. The red is decreasing, green is increasing. You see, it's decreasing on interval minus infinity to negative 0.9. It's also decreasing on interval 2.3 to 5. That's what I wrote. Decreasing. Let's make it smaller a little bit so you can see more of it. There we go. See, decreasing on interval negative infinity to negative 0.9 together with interval 2.23 and 5, and then decreasing, and then increasing on green one, increasing on negative 0.9 to 2.3, and also increasing from 5 on. So that's it. Okay. So I put all of this information on my notebook here. See, this picture, of course, is not really accurate. It doesn't have to be accurate. It's just some reference picture. I could have done a better job on this graph, but maybe in the future. And is it decreasing on these intervals and increasing on that interval? And that's really so. Watch this video over and over again if necessary to make sure you understand what you have to do next time. Alright, this next topic we're going to discuss here is the concept of even and odd functions. Even and odd. So what do you mean by an even function? By even function, you basically mean a function whose graph is symmetric with respect to y-axis. You see, something like we just draw one picture for you, something like this. You see, I'm not sorry. This is not the right one. Well, I have one right here. You see, but why should I go anywhere else? Like this graph here. You see, if you look at y-axis, everything you see on the right side of the y-axis is the same as everything you see on the left side. Actually, if you fold your paper along y-axis, everything coincides. So it's like something like this. If I just draw one simple one, let's say something like that. See, so if I fold my paper along y-axis like the y-axis like this, hopefully if I had done it very correctly, see. So if I fold my paper right here, we didn't do a really good job. This is y-axis. See, if I fold everything, then everything coincides. Okay. If this happens, you say your function is even. Okay. So when that happens, we do a simpler one for the sake of discussion. You see, something like something simple because I want to do the discussion. This is even, okay? So that means that if you choose one x value here, and this is your y value. You see? Now if you choose the opposite of x, which is negative x right here, this one is also gives you the same y value. So this point is negative x and y, this point is x and y. So clearly that means that if you change your x to negative x, the y value doesn't change. Which in notation simply says, if I have f of negative x, this point right here, this is x, this point is, the y value is an f of negative x. So y is f of negative x. This height is f of negative x. See, this height here is f of x. So if I change x to negative x, you see, if I change this x to negative x, these two are the same thing. F of x, f of negative x, which is this height, which is y, is the same thing as f of x, which is also y. So if you want to determine whether a function is even, if you have the graph, clearly you can very easily see whether your graph is symmetric with respect to y-axis. You say yes, it is even. If you have the equation of the graph, you have two choices. You can graph it, then look at the graph to see if it's even, or replace your x by minus x to see what happens to y. If y doesn't change, then the graph is even. On the other hand, if you have a graph like this one here, you see, this one is odd. Simply see, everything you have on the left side is exactly what you have one on the right side of the y-axis, but flipped over. See, so that means that if you fold your paper along x-axis and then along y-axis, then everything coincides, then your graph is odd. So let me just do one here, one simple one. Try to be as neat as I can. You see, let me just do something like this. You see, I say this is odd. Why? Because if I go ahead, fold my paper along x-axis like this, you see, then this graph, in fact, what I have to do is I will just put pencil on it, pencil, you see, put pencil so you can leave a mark. If I make this one pencil, the whole thing pencil. If I fold it along the y-axis, on it with my nail like this. Hopefully it will leave a mark. You see, you get, so if I do that, then you get something like that, see? And see, you get that. Then if I fold my paper along x-axis, everything coincides. You see, if I do this, everything coincides. Clearly. See, everything coincides. So the first thing you do, you fold along y-axis. You get this guy, and then you fold along x-axis. Everything coincides. If this happens, then your function is off. Okay, so just like this. So again, for the sake of discussion, let me just choose something simple. If I have something like this and this is off clearly. You see, if I fold twice, everything coincides. If you choose one x, then this height here is f of x. This point is x and f of x. And then if you look at the opposite of x, which is right here, negative x, then this point is negative f of x. And then clearly this height here in length is equal to this one, but opposite side. So that means this is f of negative x. So f of negative x, which is this height here, is minus of this height, f of x. You see? So that means that if you change your x to minus x, your y becomes minus y. So what's the difference then? Let's just compare these two. If you have an even function, you're changing x to minus x, y doesn't change. But if you change x to minus x in your odd function, your y also changes sign. So change x to minus x, y remains the same. If you change y to x to minus x in an odd function, then y also becomes negative y. For example, let me just write one question here first. So let me read this and then I'll give you one example. See, this also means that when we change x to minus x, the corresponding y value will not change. So if point x, y is on the graph of the function f of x, then point negative x and y is also on the graph of f of x. Okay, so if point x, y is on the f of x on the graph, point negative x, y is on the graph as well. For example, if f is even and 2, negative 3 is on the graph, then negative 2, negative 3 is also on the graph. See, if I change my x to minus x, the y doesn't change. So if this point is on the graph, this point would be on the graph as well. So if you have a multiple choice test and there are 4 questions, 4 answers, this is the right answer. For example, it says answer A. Use this one. Answer A. This point is on the graph. B, negative 2, 3 is also on the graph. C, 2, 3 is on the graph. And D, 3, 2 is on the graph. So you have 4 choices. What do you say? F is even and this point is on the graph, so which one of these 4 answers is acceptable? This is the acceptable answer, you see. But if it was odd, if I change even to odd, then which answer would be right? This answer would be right for odd. If you change 2 to negative 2, negative 3 has to be opposite, becomes positive. Okay. nested, meaning of even and odd. So based on these, we can clearly tell which one of these four graphs is an even function and odd function. See, this one is even, this one is odd, this one is odd, this one is even. Now a graph doesn't have to be even and odd, could be neither one. Like, you know, if you graph, if I have a graph that looks like this, you see, this is neither even nor odd, so it doesn't have to be either one. So sometimes the graph is even, sometimes odd, sometimes it's even. Let me see what's the next page. Let's see, I have one more example here. So, now those were the graphs. What if you have equation? Then how do you determine whether it's odd or even? Well, you have the choice. You can graph them, and by graphing you can tell whether they are even or odd. So let me maybe show this one. Is this odd or even? Well, all you have to do is to go ahead and graph it. 3x to power 2 plus 4. Plus 4. So I'm going to use regular 10 to 10. This is a window minus 10 to 10, 10. Okay. So as you can see, it's even. So even by graphing. How about non-graphing? So what I say f of negative x is equal to, I have to replace x's by negative x. So 3 times negative x squared plus 4. But when you square a negative, you get positive. So this becomes again 3x to the 4 plus x to the second. Continue here. Equal to 3x squared plus 4. See, this square killed this minus, and 3x squared plus 4 is still f of x. So f of negative x turned out to be the same as f of x. So this is even. How about this one? Well, let's graph it to see whether it's even or odd. Well, I'm sorry, this is pain. You can see it. So, clear. X to power 3 minus 2x. You see, this is odd. Symmetric if you fold it twice. In fact, if I change my window, you can see it better. Minus 4 to 4, minus 4 to 4. You see, this is clearly odd. If you fold it twice, you get odd by graphing. Now if I do it without graphing by calculations, I have to look at g of negative x. G of negative x means replace x's by negative x. Okay, this is equal to, then because you have a negative here and power 3, this negative will not go away, so you get negative x cubed, and then minus times minus, you get positive 2x. Now if you go ahead and factor a negative sign, you see, you get x cubed minus 2x. And this x cubed minus 2x is g of x, so you have negative g of x. So as you can see, g of negative x became negative g of x, and this is odd by definition. Again, this function is neither one. If you graph it, let's look at the graph here. You see, you have x to power 3 minus 4x. I always do that. Minus 4x to power 2 this is neither one actually. So if I say zoom 6, go to standard window, see, this is neither odd or even. So neither one. Not odd, not even. The same thing here. If you graph this, not odd, not even. Okay. I'm not gonna do this application problem here, so don't worry about it. Maybe we should do it. Let's see. We have a box. Well, look at something here first. Okay, this is one typical application problem that uses the idea of local minimum, local maximum. So what we have, I already wrote on these, so let me just cover it if you don't mind. Here we go. See, what I have is a box, and this box has a height of x, length of x plus 3, and the width of 7 minus x. So as this x changes, the length and the width will change, so as a result the volume will change. So somebody maybe says, okay, here we go, this box, and I can offer you to fill it up with gold shaving for free. So since you want to make the most money, so you want to get the most gold possible, so you make sure this box you create here has the maximum volume, so you get the most gold, right? So so the question therefore is, what should the value of x be for the volume of this box to be maximum? First of all, x is the height, it cannot be negative, so it's always bigger than 0, for sure. And then if you use the formula for a box like this, the formula is length times the width times the height. So this is the formula for the box, okay? So the question then that comes down to figuring out for what values of x this v would be maximum. V, I could use y instead of v to be more familiar to you, but it doesn't matter. So what you do, you go ahead and put this in your graphing calculator and graph it. You see? So I already did that. So let me make this one bigger so you can see it. Here we go. X plus, see, x times x plus 3, x plus 7 minus x. I put that in my calculator, and then I chose the window to be negative 10 to 10, and the y value minus 50 to 150. After playing a little bit with it, you know, as I said, there is no formula that tells you what window to use for what problem. You just have to do it by trial and error to get the graph to a point that you really like, so you can see the main feature. So if I say graph, this is the graph of this function, okay? And as I said, since x is positive, you just want to have, you're going to just want to have deal with this part. See, this x, for this part x's are positive, this one x's are negative, so we don't deal with that. So you want to know for what value of x here, somewhere here, you get the height, which is the volume. The height represents the volume, would be the maximum. You see the maximum. So yes, we've done this before. You have to go to second trace, and then I go to number 4, and then I put this cursor on the left side. See, left bound, say enter. You put it on the right bound, right side, and then you guess. You get these numbers. So that means if you look at bottom of the screen, it says that if you choose your x to be about 4.3, your y value, which is the volume, which is your v, is about the maximum of 84.8 if you round it up. Okay. So how do I write this? I go ahead and say, I have already written this down. According to my graph, if I choose x to be 4.3, let's say inches, could be whatever the unit is. I chose it to be inches. The volume of the box I create is maximum of 84 square inches. Okay, so let me reduce the size here a little bit. Oh, bigger, sorry. There we go. See? So if you choose X, this height, so if I choose this X to be about 4.3 inches, and then the height, of course, this would be 7.3 inches, and then 7 minus that, okay, 7 minus 4.3. So if I choose this one about 2.7, see. So if I choose X to be that much, then X plus 3 is this much, and this side would be about 2.7 inches. This box has a maximum volume, so you can go ahead and tell that person, please fill it up with gold shaving as you promised. So you're going to be a rich person. Okay. So this concludes this section. Please go ahead and watch this video as many times as you need to until you master the topics, and then go to your homework assignment and do them as quickly as soon as possible. Good luck.